Hello, hello, hello. Welcome to AP Physics video today. All right, so what I'm going to be doing today, I am going to solve some problems, the problems that I posted on the feed. I am not collecting that, uh, but I am going to go over these answers so we can move on in the notes and get to free fall. Free falling. It's a beautiful song. Tom Petty. Yeah, he's a good one. All right, so whenever you need to pause the video to catch up on the notes, go for it. But I will move through these pretty quickly. Like I said, pause the video when you need to. All right. So the first thing I like to do in every single problem is write down everything I know and what I am trying to solve. Okay. So in this example, Jim and Cindy decide to enter an engineering competition. They need to build a toy plane that will be able to accelerate fast enough to take off a runway. The plane starts from rest. Oh, okay. Starts from rest. So my velocity initial, 0 meters per second. And drives the length of the 15-meter runway. So the displacement is 15 meters. It needs to lift off at a speed of 20 kilometers per hour. How fast must the engine be able to accelerate? So I'm trying to solve for acceleration. Okay, so I have everything I need written down. Okay, I'm going to zoom in a little bit. Have everything I need written down. Now, first and foremost, there's a trick. There's kilometers per hour. Okay, so I'm going to convert that real fast into meters per second. Okay, and in meters per second, that should be about 5.5 repeating. Okay, 5.5 repeating. Okay, now once I got that far, I have to pick an equation. Okay, have to pick an equation that fits my criteria. So what I always look for is t for time. Do I have t for time over here anywhere? No. So I cannot use that equation. Once again, t for time. I cannot use second equation. So the third equation has this right here. So I'm going to use v final squared is equal to v initial squared plus 2a delta x. Okay, there we go. All right, now I just plug in my numbers. Okay, velocity final squared. Okay, so 5.5 repeating squared is equal to 0 squared plus 2a times 15. All right, and when you eventually solve for a, you'll get 1 meters per second squared. Okay, and that's how you will solve that one. Okay, question number 1. All right, hopefully that kind of made sense. All right, let's move to question number 2, 22. All right, there we go. Cindy is frustrated and leaves the competition without Jim. She is driving on a road going, 11.4 meters per second. I'm going to write that down. So my initial velocity is 11.4 meters per second. Okay. And suddenly sees a deer. Cindy immediately applies to the brakes to slow down with an acceleration of 3.8 meters per second squared. Now, since she's slowing down, I knew you caught it. All right, since she's slowing down, it's negative 3.8. If the deer is 10 meters from Cindy, when she applies the brakes, does she hit the deer? All right, so we're going to find out that her velocity final, she's slowing down. She's trying to stop. So her final velocity is going to be 0. And we're trying to see how far she goes. All right. Does she go greater than 10 meters and hit the deer, or less than 10 meters and not hit the deer? All right. So I have my unknowns and knowns. Okay. So when you plug it into your, let's see, which equation are we going to use? Once again, this has time. I do not. This has time. I do not. So I'm going to use my one equation again. So velocity final squared is equal to velocity initial squared plus 2a change in displacement, 2a delta x. Okay. So velocity final, 0 squared is equal to my velocity initial, 11.4 squared, plus 2 times negative 3.8 times the change in displacement. Okay. So 11.4 squared is 129.26. So 0 is equal to 129.96. Okay. Minus 7.6 delta x. Okay. I'm going to subtract the 129 over. And divide by negative 7.6. And my final answer is 17.1 meters. Okay, 17.1 meters. Does she hit the deer? Well, the deer was only 10 meters from her. So yes, she did hit the deer. Okay, so the answer to A is yes. Now B says, if she did hit the deer, what speed did she hit it at? Oh, okay. Once again, got to write my known. So my velocity initial is 11.4. If she did hit the deer, I don't know what my velocity final is. All right. I know my acceleration is negative 3.8. And I actually know my x. How far was the deer from me? The deer was 10 meters from me. Okay. All right. Now, got to look at my equations. Once again, has time. Once again, has time. So I'm going to use the same equation I've been using. Velocity final squared is equal to the velocity initial squared plus 2a delta x. Okay. So my velocity final squared, still don't know what that is. 11.4 squared from the previous, I knew that's 129.96, plus 2 times negative 3.8 times 10. All right. And if you plug that all in the calculator, VF squared is equal to the square root of 53.96. So the velocity final ends up being, I got 7.35. So if I round to sig figs, 7 meters per second. Okay. So she hurt the deer pretty bad, huh? Okay. So that's 22. 23. Harry leaves his house and starts to sprint where Cindy is. If Cindy is 400 meters away and Harry is running out the door, all right, so let's write down my information. Cindy is 400 meters away and Harry is running out the door at 2 meters per second. So my initial velocity is 2 meters per second. And with an acceleration of 0.2 meters per second squared. Okay. How long will it take to get to Sydney? Ooh, I have time. How long? Okay, so I got to look at my equations. Now, clearly I know I'm not using my third equation because my third equation doesn't have time. I got to use one of the first ones. Okay. Now, I have displacement. I have initial velocity. And I have acceleration, and I'm solving for time. So I'm going to use the second equation. Okay. So x. Well, I'm going to do delta x. Rearrange the equation a little bit. Delta x is equal to the initial velocity times time plus half the acceleration time squared. Okay. So I'm going to plug in. I got 400 is equal to my initial velocity was 2t, plus half the acceleration. So that's going to be 0.1t squared. Okay. So what I'm going to do is I'm going to rearrange my equation here. So I'm going to have 0.1t squared plus 2t minus 400 equals 0. All right. Now, tricky. All right. We got to solve for t, so we got to do the quadratic formula. All right. So in the quadratic formula, what that looks like is negative b plus or minus the square root of b squared minus 4ac all over 2a. Beautiful. All right. So I'm going to need another index card. Negative b, so I got negative 2 plus or minus the square root of 2 squared, which is 4, minus 4 times a times c. 4 times a times c, I got a negative 160. All right, so I have my negative all over 2a. Which is 0.2. Okay. Now, I'm not going to use the negative value here. I'm not going to use the negative value because I'll show you real quick. The square root of that is 12.8 all over 2a. And the reason because he's running forward, okay? Since he's running forward, I'm going to use the positive, okay? So I'm going to add those two together, which gives me 10.8 over 2a, or 0.2. I don't know why 0.2. All right. And if you add those two divided by 0.2, I got 54. But if I round to sig figs, it should be 50 seconds. Okay. That one's a little trickier. All right. How to implement the quadratic formula into that problem. Okay. A few more left. All right. Jim, who was left at a competition, gets his bicycle and starts heading home. He coasts due west 8 meters per second. Okay, so his initial velocity is negative 8 meters per second. At one point, he encounters a patch that is 7.2 meters across. So if he's traveling left to right, so he's traveling negative 7.2 meters. Okay. By the time he leaves the sandy patch, his speed was reduced to 6.5 meters per second. Okay. Assuming the bicycle slows at constant acceleration, what was his acceleration? Do I have time in this problem? I do not. So hopefully you know what equation I'm going to be using. You knew it. I'm going to be using my third one. Okay. Velocity final squared is equal to velocity initial squared plus 2a delta x. All right, my delta x is negative. Okay. Hopefully that helps you out solve that problem. When you plug it all the way through, you should get, I got 1.51, but looking at sig figs, your final answer should be 2 meters per second squared.
Mr. Yost, copper 045.
All right, now we hit
Ms. Boyd,
Sorry
please
for
call
all these
4045.
announcements. All right, now we have the home run question. All right, this is a toughie. All right, so a speeder who's doing 40 miles per hour, but what I'm more focused on, is doing 17.9 meters per second. Okay, so that was the initial velocity. Okay, in a 25 mile per hour zone, approaches a parked police car. The instant the speeder passes the police car, the police begin their pursuit. The speeder maintains a constant velocity, and the police car accelerates. So this is the speeder. It's going to be the police car over here. The police car accelerates with a constant of 4.5 meters per second squared. Its initial velocity was 0. All right. How long does it take the police car to catch the speeder? Well, so I'm trying to solve time. Now, to catch them, my displacement is going to be the same, right? Oh, my displacement is going to be the same. X is going to be equal to X. So I got to look to see what equation I want to use, okay? Where I have, all right, now I have time, acceleration, initial velocity, and X. Now, that's going to be my second equation. But since X is equal to X, okay, what I'm going to have is my initial velocity times t plus 1/2 a t squared is equal to the cop side initial velocity t plus 1/2 at squared. Okay, so my initial velocity over here was 17.9 times that by t. So if I kept a constant acceleration, or constant velocity, constant velocity, this car was not accelerating. Acceleration is 0, so all of that times that is just 17.9 is equal to, my initial velocity here was 0. My initial velocity here was 0. So 0 plus 1/2 the acceleration, 1/2 of 4.5 times t squared. Okay, so if you plug that in here real quick, 17.9 t is equal to 2.25 t squared. All right, so if you divide by 2.25 t, divide by 2.25 t, the t's cancel. I am left with 7.96 is equal to t. So sig figs, 8 seconds. Okay, so that was A. That was tricky. That was a tricky one. B says, so I'm going to keep that information. B says, how far have both cars traveled in this time? So I want to know what X is. All right, I'm just going to choose X. All right, and I'm just going to use that same equation. So X is equal to the initial velocity of t plus 1/2 a t squared. Okay, so I'm going to do the cop car. All right, just to see. So X, my initial velocity of the cop was 0. So that's going to be 0 and 0. Okay. And then 1/2 the acceleration, 4.5, times it by the time it took squared. So my time was theoretic, in reality, 7.96 squared. Okay. You plug that in your calculator. X is going to be equal to 100. I got 142.5, but I only need 2 sig figs. Okay. So that wasn't too bad. Wasn't too bad using the same equation. Okay. And then the third question says, what is the velocity of the police car when it reaches the speeder? All right, so I need to solve for my final velocity. That's what it's asking for. Okay. So when it's asking for final velocity, which equation am I going to use? I'm going to use my final velocity equation. Okay. So let me plug it in real quick. My velocity final squared is equal to my velocity initial squared. Let me get rid of all those. Velocity initial squared plus 2a delta x. Okay. So I got to know my final velocity. I know my initial velocity was 0. I know my 2. I know my acceleration was 4.5. And I know my x now. My x was 142.5. Okay. If you plug it in, take the square root, the final velocity, I got to be 35.8. But if you look at sig figs, 36 meters per second. Okay. All right. Last problem. All right. Assume that the brakes in your car create a constant deceleration. How fast would you be going if you double your driving? All right. Now, this is a little tricky one. All right. So it's asking if you double your speed. Okay. Double your speed. So I'm going to have an initial velocity initial. Velocity final is going to be, all right. It's asking for time and acceleration. Okay, so what equation am I going to use? Acceleration, I'm going to use my top equation. All right, we haven't used my top equation yet. This is a good one to use it on. All right, so the equation is velocity final minus velocity initial, just rearranging, over acceleration is equal to time. I rearranged that top equation to get time by itself because it says if you double the speed, all right, if you double the speed, how does this affect the time required to come to a stop? Okay, so if I'm coming to a stop, my final is going to be 0. Velocity initial over A. All right, so negative V. So if I double this side right here, if I double that, the time required is also going to have to double. They are directly related. Okay, so answer for A is double. Okay. For B says the distance it would be required to stop. So now I have to solve for X. So once again, I know my velocity initial, velocity final. I know my acceleration, and I'm solving for X now. Ooh, so I don't have time, so I got to use this third equation. Okay, so velocity final squared is equal to velocity initial squared minus 2a delta x. Okay, what I'm going to do is I'm going to rearrange this to solve for x. So I'm going to have velocity final squared minus velocity initial squared. And then I'm going to divide that by negative 2a equal to delta x. Now, once again, my velocity final is 0. Okay, so here, if I put a 2 in front of my velocity, negative 2, this value is being squared. So negative 2 squared actually affects this to the 4th power. It's quadrupled because negative 2, and you're squaring that value. It's quadrupled is your answer. Okay. Hopefully that started to make a little bit of sense. You start to understand what equations go where. And once you figure out the equations, you are golden. Okay. And you'll be able to figure it out. Okay. Anyway, I hope you guys have a great day. We're going to continue learning about acceleration, mainly in free fall. And then after free fall, we're hitting pretty close to the end of the chapter. It's pretty smooth sailing. Okay. So anyway, I hope you guys have an awesome day. Keep up the hard work, and we will talk to you later.